Okay, let's get into this. There have been some pretty big claims floating around about AI models, right? Specifically, large reasoning models, LRMs.
Yeah, this idea that they just kind of collapse, completely fail when you give them complex planning puzzles that get, well, a bit too tricky.
Exactly. But today we're diving into a paper that really questions those claims. It's called The Illusion of Thinking. Catchy title.
It is, and the core idea is fascinating. It argues that maybe these failures we saw, maybe they weren't about the AI's reasoning hitting some fundamental limit at all.
But more about flaws in how the tests themselves were actually designed.
Precisely. You had earlier work like Shojaee et al. Painting this picture of LRMs just, falling apart on things like Tower of Hanoi or river crossing puzzles past a certain point.
Right.
But this new analysis is suggesting, hold on, maybe we were measuring the wrong thing. So our mission here is to unpack this paper's argument.
Let's see if these models are maybe more capable than some tests showed and what that really tells us about, well, how we evaluate AI in the first place.
And the paper kicks off with something pretty striking. They found evidence that the models themselves seem to know when they're running into an output issue, not necessarily a thinking issue.
Okay, explain that. How would a model show it knows that?
Well, think about tasks like Tower of Hanoi. To solve it fully, especially with more disks, you need to generate these incredibly long lists of moves.
Right, it gets huge fast.
Exactly. So this paper points out that when people replicated some of these tests, they mentioned someone on Twitter, at Scaling01, who captured this, you'd actually see the model saying things like, oh,
Like what?
like, the pattern continues, but to avoid making this too long, I'll stop here, or variations on that theme.
Wait, seriously. So it knows the pattern, it knows the next steps, but it's essentially saying, look, I'm not going to sit here and type out 10,000 moves for you.
That seems to be exactly what this analysis is suggesting. And think about what that means for evaluating them, right?
Yeah.
Automated systems are often just looking for that perfect, complete, step-by-step answer. If the model cuts it short, even if it says why.
The system just marks it as a failure. Total failure.
Bingo. It mistakes a practical output limit, the model basically saying, I can't type all this for a breakdown in reasoning.
Huh.
And the paper argues this kind of undermines those ideas about, like, the statistical inevitability of failure on long sequences because it shows the models aren't just dumbly generating tokens hoping for the best. They can adapt, they can manage their output.
Okay, that alone really changes how you might interpret some of those collapse results. If it's a typing limit, not a thinking limit.
Wow. It's a fundamentally different interpretation.
So okay, hitting output limits, that's one big way the evaluation might have been misleading. What was the next major issue this paper flagged in the original experiments?
This next one is, well, it's pretty fundamental. It's about the river crossing puzzles they used.
Okay.
So the original study tested versions of river crossing with 6 or more agents, people, cannibals, whatever, and a boat that could only hold 3.
N equals 6 or more, boat capacity 3. Okay, what's the catch?
The catch, as this paper points out, citing established puzzle theory, like from Efimova back in 2018, is that that specific version of the puzzle, greater than 5, boat capacity 3, it actually has no solution. It's mathematically impossible.
You're kidding me. They were testing the models on unsolvable puzzles.
That's what the paper claims, yes.
And then marking them down as failures for not solving the impossible.
Pretty much. The paper uses a good analogy. It's like giving a math solver an equation with no solution and then penalizing it when it correctly tells you, hey, this thing's unsatisfiable.
Wow.
The original evaluation, it seems, didn't check first if the puzzle instances were even solvable. It just fed them to the models and graded them.
That feels like a pretty big oversight. You can't really blame the model for that one.
You really can't. It's trying to do something literally impossible based on the rules given.
Okay, let's swing back to Tower of Hanoi then. You mentioned the output limits, the typing problem. Does this paper get into why that specific task in that format blew up the token limit so badly?
Oh yeah, they dig into that. The issue was how the original evaluation was set up. It demanded that the model output the entire sequence of moves needed to solve the puzzle.
The whole thing.
At each step of its response.
Yeah.
Not just the final answer, but the full list, repeatedly. And this format, they show, leads to what they call quadratic token grew.
Okay, that sounds like it gets really big really fast.
It does, exponentially many moves. But the representation required grew quadratically with the number of disks, n. They estimate about 5 tokens per move step in that specific output format.
Okay.
So TNN, the total tokens needed, grows roughly like n squared. And what that means is, with typical token limits on models, say 64,000 or 100,000 tokens.
Yeah, the context windows.
Right. The models physically cannot output all the required steps for Tower of Hanoi problems bigger than maybe N7 or N8 disks, not in that format.
So it's not that they couldn't figure out move 5,832.
It's that they literally couldn't type out the full list containing move 5,832 and all the others within their character budget, so to speak.
And crucially,
if you look back at the original study's results, the point where performance reportedly collapses, it happens right around that N7 or NA8 mark.
exactly when the required output length in that specific format starts hitting the token ceiling.
That's the strong argument this paper is making. The observed limit wasn't necessarily on planning, but on enumerating that plan exhaustively under a super demanding output requirement.
Okay, this is really starting to paint a different picture. So if that's the case, did this paper find any proof that the models can handle these bigger problems if you just, ask them differently, change the format?
They did some preliminary tests on exactly that. They took a few different models, Claude 3.7 Sonnet, Opus 4, an OpenAI model, Gemini 2.5.
Okay, current models.
Yeah, and they tested them on a much bigger Tower of Hanoi problem, N15 disks.
15, that's way past the N7 or 8 limit you just mentioned for that quadratic format. How could they possibly output that?
They couldn't, not in the old format, so they changed the prompt.
Right.
Instead of asking for the full list of moves,
They
asked the models to generate a simple Lua function that prints the solution when called. Basically, give us the code, the algorithm that generates the solution, not the full solution itself right now.
Asking for the recipe, not the finished dish. Smart. What happened?
They reported very high accuracy across tested models for N15.
Wow.
And get this, the code the models generated, it was typically under 5,000 tokens.
Under 5K tokens
Yeah.
for N15. Compared to what would it have been in the old format? Astronomical.
Colossal, unmanageable within current limits. So this really shows, according to the paper, that the models do retain the core recursive algorithm and the reasoning capabilities. They understand how to solve it.
They just choked when forced into that super long, exhaustive output format because of token limits.
Exactly. When they weren't burdened by that specific enumeration requirement, they could demonstrate the underlying competence.
If we connect this to the bigger picture, it really hammers home how much the way we ask the question matters, doesn't it?
Absolutely. The output format, the representation you demand, it can totally change what you observe about the model's abilities. It's not just can they solve it, but can they express the solution in this one, very rigid, very long-winded way within their practical limits.
It is such a critical point for anyone testing these things. Okay, the paper also had issues with how the original study measured difficulty, right? Something about compositional depth or number of moves.
Yeah, they argue that just using the number of steps in the solution as your main metric for difficulty is, well, misleading. It conflates mechanical execution with problem-solving difficulty.
Okay, unpack that for me. How is the number of steps not related to difficulty? Seems intuitive.
It seems intuitive, but think about it this way. The paper contrasts Tower of Hanoi with problems like river crossing or blocks world.
Okay.
For Tower of Hanoi, yes, the solution length is exponential 2 to the n-1 moves. It gets incredibly long. But the decision you make at each step, it's dead simple. There's basically only one valid move you can make. The branching factor is 1. You don't need to search or plan ahead complexly for each move. The logic is trivial, like O1, complexity. Always the same easy choice.
Okay, simple decision. Just repeated many, many times. Got it.
Now, look at river crossing or blocks world. The solution length might be much shorter, maybe like 4n or 2n moves.
Shorter solutions.
But the decision at each step, much harder. The branching factor is way higher. There are many possible moves. Most are bad. You need complex search. These are NP-hard or PS-based problems. Finding the right sequence requires exploring possibilities, checking constraints. It's computationally intensive thinking at each step.
Ah, I see. So Hanoi has lots of easy steps, while river crossing is fewer, but much harder. Steps requiring real search and planning.
Precisely. And this explains that seeming paradox. Why could a model maybe pump out 100+ simple Hanoi moves correctly, but then fail on a 5-move river crossing problem?
Because those 5 river crossing moves involved way more complex reasoning and search than the 100 simple, almost mechanical Hanoi moves.
Exactly. So just counting the number of steps in the final solution is a poor proxy for how hard the problem actually is for the model to figure out moment to moment.
That's a really important distinction. Okay, let's try and pull this all together then. What are the main messages this source paper wants us to take away about those original claims of LRM reasoning collapse?
Well, I think there are three core points. First, models hit practical token output limits, and this can look like reasoning failure when it isn't, especially on tasks needing long outputs in specific formats.
Right, the typing versus thinking issue.
Second, automated evaluations can be seriously flawed. They might misinterpret model behavior like truncation, and crucially, they sometimes don't even check if the problems they're testing are possible to solve.
The unsolvable puzzle problem, yeah.
And third, simple metrics like just counting the solution steps don't capture the real problem-solving difficulty. They ignore the complexity of the actual decisions or search involved.
So, for someone listening trying to make sense of what these models can really do, what's the bottom line here?
The bottom line, according to this paper, is that those earlier findings of an accuracy collapse probably don't show a fundamental ceiling on the model's reasoning power itself.
Okay.
Instead, they're better seen as valuable engineering insights. They teach us about how current models behave under specific, sometimes flawed, test conditions. They highlight just how careful experimental design is.
So the paper isn't saying the models are perfect reasoners.
Not at all. But it's strongly arguing that those specific results don't support sweeping claims about fundamental reasoning limits. We just need much, much better ways to test them, ways that can actually separate the reasoning part from the output generation part and from flaws in the test setup itself.
Which leads right into their suggestions for the future, right?
Yeah.
How should we be doing this better?
Yeah, they offer a few clear guidelines, design tests that consciously try to distinguish reasoning from output constraints. Always verify puzzle solvability beforehand sounds basic, but apparently necessary.
Don't test the impossible. Got it.
Use complexity metrics that reflect the actual computational difficulty, the search space, not just how long the answer is. And consider testing with different ways for the model to represent the solution, like asking for code instead of the full step-by-step list.
See if they get the logic, even if they can't type out the whole War and Peace version of the answer.
Exactly.
And they wrap up with a question that really crystallizes the whole issue, doesn't it?
It does. It's basically the core idea from their title, phrased as a challenge to us.
What is?
The question isn't whether LRMs can reason, but whether our evaluations can distinguish reasoning from typing.
Oof. Whether our evaluations can distinguish reasoning from typing. That really reframes how we should think about AI limitations, doesn't it?
It puts the onus back on us, the evaluators.
Yeah. This whole deep dive into this one paper really drives home how the tools we use, the methods we choose, can fundamentally shape what we think we know about AI capabilities.
It makes you wonder, right? Thinking about how easily these evaluations might have misinterpreted things, what other limitations might we be wrongly blaming on the AI models themselves today?
Just because of how we're measuring them.
Exactly. What does that mean for how you, listening now, should approach understanding what AI can truly do going forward? It's a huge challenge, not just for the AI researchers, but for anyone trying to grasp these incredibly complex systems.
Evaluating complexity, whether it's human or machine, it's always trickier than it looks on the surface.
Definitely something to chew on.